Hello everybody, my name is Halo. Welcome to this video. In this video, we're going to be looking at round robin CPU scheduling algorithm. See, round robin CPU scheduling is quite a tricky algorithm, okay, but it is not hard. We just need to understand a few things, and once that basics, that fundamentals is clear, I think it's very easy to code. We'll go ahead, we'll go step by step on how we are approaching this problem. We'll go with what we are dealing with. We'll work out an example, we'll calculate the turnaround time, waiting time, everything. We'll calculate the boundary conditions, then we'll move on to the code so that you guys can understand it very easily. Okay, so with round robin CPU scheduling, there's one thing that you have to understand, that all the processes share the CPU. What does this mean? See, in every single algorithm, the CPU is being shared only, so that is not something that's new for us. Okay, once one process completes, another process completes. In case it's a preemptive algorithm, once one process is interrupted, another process is interrupted. Okay, so that is not what we are talking about here. We are saying, see, in those cases, those are simple interrupts only. Here, the CPU itself is shared. That is, there's kind of a routine where all different processes are being shared by the CPU. Okay, so if we have, for example, in the left, we have P1, P2, P3, P4, P5. All P1, P2, P3, P4, P5 should be given equal amount of sharing time and in the system. Okay, so that is how it works. How will you give equal amount of time? That we'll look at. See, for example, I have process P1, P2, P3. Let's say all of them arrive at t is equal to 0. Okay, and this has a burst time of 4, this has a burst time of 6, this has a burst time of 2. How round robin works is, see, P1 is being executed, then P2 will be executed for some amount of time, then P3 will be executed for some amount of time, then again P1 will be executed for some amount of time, P2 will be executed, and P3 will execute. This will keep going on till either P1, P2 or P3 finishes, and this order will be, for example, P3 has finished now, we'll just do P1, P2, then P2 will finish, then we'll just do P1 because there's no other process for the system to share, and finally everything will be completed. Okay, now what, so again I said for some amount of time P1 will be there, some amount of time P2 will be there, some amount of time P3 will be there. What is this some amount of time? That is what we need to answer, and the answer is nothing but time quanta. What is a time quanta? Look, until now, even the preemptive algorithm that we have been working on will be saying from t is equal to 0 to t is equal to 1. That is the time interval between two processing states, kind of, in the time is 1. That is, say if P1 is going from 0 to 1, P2 will be going from 1 to 2, or P1 again will go from 1 to 2. So the 0 to 1 is the time interval. Okay, what is time quanta? Time quanta is the same as the time interval, except it is not necessary it will be 1. So this can be a time quanta, this can be a time quanta, or 0 to 3 can be a time quanta, 4 can be a time quanta, 5, 6, 7, 8, 9, 10. Anything you want, you can give as a time quanta. Okay, so the same example, let us take a time quanta equal to 2. How will this work out? Okay, so P1 goes from 0 to 2, and P2 goes from 2 to 4, P3 goes from what? 4 to 6. That means P3's burst time is now over. Again we come to P1, that will execute from 6 to 8, P2 from 8 to 10, P3 is already done, no need. Again we have P1. See, P1's burst time is 4, already 1 executed, so P1 is also gone, which means only P2 is remaining. P2 has been executed once, twice, and finally the third time, that is to match that 6. So from 8 to 10 and from 10 to 12, P2 will be there. So we can go ahead and get rid of all these things. This, yeah. So this is how the round robin method will be there for these particular processes. Okay, this again is assuming all of these arrival time is 0. So what do you do if they have a different arrival time? Because the entire point is the CPU should share every process equally. How will you share the process equally when they arrive at different times? See, look, one must always keep in mind that if a process arrives later, okay, it should be given first priority. See, I'll tell you how. Let's say, again time quanta, let it be 2 itself. Let's say this process arrives at t is equal to 0. Okay, this process arrives at t is equal to 2. Okay, and this process arrives at t is equal to 4. Now at t is equal to 0, you only have one process, P1. Okay. Now, so there's no other process. So obviously CPU will only execute P1. P1 will be from 0 to 2. Okay. But at t is equal to 2, we have process P1 and P2. But P1 has already been there once, which means P1 should again not execute. P2 should be given the chance now, correct? Because now it should be shared. P1 cannot hog twice. So P2 will be shared. Okay. Now at t is equal to 4, we have P1, P2, P3. Okay. But P2 has already been given a chance. P1 has already been given a chance. So P3 must be given a chance now. Okay. So that is what the major concept is. That is how we are going to share it equally. Okay. So with this being in mind and the idea of time quanta being in mind, I hope that was you guys could understand that. Let us go ahead and work out an example so that you guys can understand what it is that we are talking about. Okay. So obviously before we go and work with an example, we must declare a time quanta for this particular box here, some time quanta. So we'll go and say 2 is the time quanta. Okay, right. So for the example, see, we have a set of processes here with their arrival time and their burst time. Okay, now we're going to see with round robin CPU scheduling how the Gantt chart will look like. Okay, that is simply what we're going to see. Then we're going to be calculating the completion time, turnaround time, and the waiting time. Now, at t is equal to 0, what are the processes that are available? When you look at it, you can say that process P4 is the one that is going to be available, correct? So P4 is going to be available for t is equal to 0, time quanta is 2. That means P4 will be executed from 0 to 2. Until this you guys can understand, right? Okay. So let us move to the next time interval, that is t is equal to 2. Already P4 will be available only because it's not yet completed. The burst time is 3. We have only executed 2, which means only one burst time is there. Okay. That again, that burst time is less than time quanta. That means there's another case we have to deal with. We'll go ahead and deal with that also in a few moments. Now, at t is equal to 2, we can see that P3 and P1 are also arriving. That is, P3, P1 are also arriving. But look, here, let us say P4 is already executed. P3 not yet executed. P1 not yet executed. Now, one thing to keep in mind is P3 arrives first, which means P4 obviously we're not going to execute, but P3 we're going to be executing next. Then we are going to be executing P1. Why? Because that is the order in which they came with. That is how we are going to execute them. Now, look, one major thing to keep in mind is if we see this particular way of arranging our list is quite cluttery. It is chaotic because this process should not be executed. This should be executed. This should not be executed. That means the first element or the last element should not be executed. So this element is we are choosing manually. Let us put this in a way that every time we can close our eyes and say the first element is the one which we are going to choose. How will we do that? See, look, in t is equal to 0, once P4 is completed, let us go ahead, put P4 in the end. Okay. Now, everything that we have here is in the same order of the arrival. P3, P1 is the order of the arrival, followed by the process that was already completed. Okay. Now, look, P3 is the first element, correct? So, in this case, P3 will be there from 2 to 4, correct? So, at t, P3 is executed now. Can we go ahead, put P3 back? Yes, we can. Great. Now, again, P1, we don't know because it has arrived already. We don't know when it is arriving. So, again, we have P, this should be empty. Okay, P1. These are the processes which are executed. Okay. These are not yet executed. See, not executed will be in the same order of execution. Not yet executed will also be in the same order of their arrival. So, at t is equal to 4. P4, P3 already executed. Okay. What else is arriving? See, P5 is arriving at 4. That means P1 has arrived first here at t is equal to 1, which is not executed here. Sorry, at P1 at t is equal to 2, not executed yet, followed by P5, correct? At t is equal to 4. These are the executed, not executed. So that means if the executed is if the not executed is empty, then only we move on to the executed. So we just move on with the example. You guys will understand as you go. It's okay if we don't understand as of yet. Okay. See, the first element here is P1, correct? That is which arrived first, which means P1 is what we're executing from t is equal to 4 to 6. Okay. Now, which means we can go ahead, remove this and put this over the back over here, correct? This we don't know yet. P5 arrives at 4. So at t is equal to 6, what is happening? See, we can see that P2 also arrives now. But P2 arrives at a later time than P5, which means after P5 only P2 should come, correct? Okay. Now, let us say, what are we going to do? See, this arrives at t is equal to 5, which means in this particular point, P5 will be executed from 6 to 8, okay? So that we know, okay? So P5 is now executed. So P5 will now be here. So finally, the only thing not executed is P2. We'll go ahead and execute P2 as well. See, P2 has a burst time of 2 only. So once we do this, we can just remove this directly from the list. No need to re-add this back because its burst time is over. P2 is completely serviced. Now, let me write this list a bit better. We have P4, P3, P1 and P5. Okay. So these are the processes which remain. All of them have been executed, but P4 has been the one which has been executed first, which means next time we give a chance, P4 will be the one which is getting a chance. So as t is equal to 10. See, the remaining burst time for P4, again I said the burst time was 3. We have already time quanta as 2 means already P4 has been executed for 2 milliseconds here, but you can take any unit if you want to. So the remaining burst time for P4 is 1. Right? So, but P4 should be the one which is next executed. In case the remaining burst time is less than the time quanta, only execute for the remaining burst time. Okay. So P4 will go from 10 to 11 because that is the only thing that is remaining. Okay. I'm recording, I was just checking if I was recording. So now P4 is also gone. Okay. Now at t is equal to 11. What do we execute next? P3, because this is the one which is backwards here when you look from here. Okay. P3 has an execution time of 8. Already once we have executed it. And when we execute it again, the remaining burst time for it will be 4. Correct? Okay. Now, once we execute P3, we have to move P3 to the back of the list again. Correct? And at t is equal to 13, the first element is what we're going to be executing. Now, look, initially we're looking at the arrival time for everything, the burst time for everything, and then we are looking at, okay, if this is arrived, this is not given a chance here, then only we meet. But now we're just closing our eyes and saying P1 is the one we should execute. Why? Because we're pushing everything to the back. By that, we are, okay, we know that whichever process is first, that means that is the one which needs the next chance. The process at the back means that is the one which has got chance very recently. Okay. So, which means at t is equal to 13, we go ahead and do P1. P1 has already been executed once, now a second time. So, it only has one more execution left because burst time is 6, time quanta is 2. Once P1 is also executed, we can go ahead and throw P1 back, which means at t is equal to 15, what is the process? P5, obviously. So, we execute P5. What is the burst time for P5? Look, burst time for P5 is 4, correct? And we've already executed this once, twice, which means P5 is now gone. We don't need to put this back in the list. I'm going to rewrite the list. P5 is not needed only. P3 and P1, which is the only things which remain in the process list. Okay. Process list, process queue, however you call it, it's the same thing only. I call it process list, but the technical correct thing is process queue or the ready queue, or I don't know how you define that, but for understanding, we're calling it the process list. Okay. Now, P3 and P1, we have two processes left. P3 is the one which executed last. So this is the first process that we're going to be executing. So P3 will be executed from 17 to 19. Look, P3 has already been executed once, twice, thrice. The burst time is 8, which means it has one more cycle left. It is not yet completed. So we go ahead and throw P3 back to the list again. Now, at t is equal to 19, we have P1. So we are going to be executing P1, but you see P1's burst time is 6, already been executed once, twice and thrice, which means P1 has been completed. Sorry, P1 has been completed. The only process remaining is P3 at t is equal to 21. So we go ahead and service P3 until its completion. So this is what the Gantt chart would look like because there's no other process. That means the algorithm is done. Now look, the algorithm itself is simple only. If you guys work this out on your own, you will be able to understand what is going on. We have been standardizing it in the way that the first element always will be the one which is being executed. Okay, so this is the round robin CPU scheduling algorithm. Let us go ahead, calculate the completion time, the turnaround time, and the waiting time for all these processes P1, P2, P3, P4, P5, and then we can move on. Okay, so if we calculate for everything, it'll take a lot of time. Let us go ahead, take some random value here. P3 will take, P3's completion time is 23. as you can see right here. Then what is the turnaround time? Turnaround time is given by completion time minus arrival time. P3 arrives at t is equal to 1, which means turnaround time is 22. That is 23 minus 1. Okay. So what is the waiting time? Waiting time is the turnaround time minus the burst time. The burst time is 8. 22 minus 8 is 14. These are the values for P3. Okay. So with this being in mind, I think we can move on to code now. But before we go to the code, few things we need to understand that how this algorithm we're going to be implementing in the Python. Okay. See, number one, this makes sense, but there are a few boundary conditions that we need to address. Okay. Number one, what if there are no processes available? No processes available. At any time, we look at what are the processes available. No process available. That is a boundary condition we need to see. Another boundary condition is what if the remaining burst time is less than the time quanta. So that also we need to see, because now if you look at it, in this case, from 10 to 11 only we're executing, we're not executing the full time quanta. That is why this is also a condition that we need to see. So these two are mainly what conditions we need to apply when we're coding. One more thing is the logic behind how we are coding. Just as here, we're looking at all the functions. See, once something is executed, we're putting it in the back of the process list, right? That is what we're going to be doing here as well. The exact same logic. Let's say if P1, P2, P3 is there, it should be executed in this order. Okay. So once P1 is gone, okay, see, if three processes we have, we say this is the order that will be executed. Okay. P1, P2, P3 and dot. Okay. Once P1 is executed, this is executed, we go ahead, put P1 to the back of the list. Okay. So what is the remaining order? This will be the remaining order, and you can see the remaining order is P2, P3, P1. Correct. So once P2 is executed, we remove P2 from here and then we add P2 to the back. Okay. Now from this is also done. So the remaining order should be this, correct? And this is the same thing. So that is why once we're processing, we're taking this from here and putting in the back of the list, so that at any point in time, since we are checking for time quantas for each time quanta, right? So for each time interval we're checking. So at any point, at any time interval, that order is what we're getting. That order of the available is the order in which they're executed. In case this, for example, P1 is not available, P2 is not available, then P3, P2 until P1 comes, then it will be first priority. Because let's say if P1 is not available, P3 will be given put to the last. Then P1 again not available, so P2 will again be put to the last. Now if say P1 is available, P1 will be the first element, not P3 or P2. So P1 will be given the chance first. That is being maintained, that is being consistent here. That is why we are using this algorithm where we remove the process and append it to the end of the queue. Once we are doing that, what does that mean? It maintains this proper consistency. Okay. If that you can understand, we can move on to the code and I'll meet you there. Right. So we have VS Code open right now. We're going to be looking at the round robin CPU scheduling algorithm. So this algorithm will obviously be taking input two things, a process list and a time quanta. Okay. So these two we have to so what is this process list? Process list is basically this particular table right here. We have the process burst time and the arrival time. This should not be in the this table entirely will be kind of a nested list. Okay. The nested list's inputs will be each row will be this particular process value. Okay. So this will be the input. Okay. But not in this particular order. We represent a process by, look, its arrival time, burst time, and the PID. Okay. This is how we are going to be representing it. I'll tell you why this specific notation we are taking in order to represent this process in a few moments. Okay. So first of all, let us go ahead and define this particular process list so that you guys know what we're talking about here. Process list. Okay. Yeah. So what is the process list? Like take this for example. So we have arrival time, burst time, and PID. So 2, 6, and P1 will be one entry. This is a nested list. So 2, 6. P1. This will be one entry. Okay. Similarly, I'm going to fill all these entries. I'll meet you then. Okay. So I actually have this entire process list right now in this particular order. You guys can go and check it out if you want to. Once that is done, what do? We go ahead and we declare the time quanta also. Let's take 2 here because that's what we work with here. And let us go and define the function which we are going to be using. Okay. The function which I've been going to use is something called round robin. We can go declare that, and we can go declare process list as the input and followed by time quanta. Time quanta is nothing but 2 in this case. Okay. So let's just go pass and let's just go and call this function so we know what we are talking about here. So go across the process list followed by the time quanta. Okay, so if we just run this right now, nothing will happen because it's a pass statement. So first things first, we need to declare a few things. Number one, we have this Gantt chart right here, correct? And then number two, we have this particular table which contains the process ID, the CT, TT, WT. So those are something we need to declare, and we have to declare this time because we're keeping track of time everywhere. So number one, time, initialize that to 0. Let us take a Gantt chart which takes which PID is being serviced. That will be a list followed by completed this table. My proposal is to keep this table a dictionary where this is the keys, and these are the values. So for each PID, there will be a list containing of CT, TT, WT, and this will be the key. Okay, so that will be a dictionary. Okay, so first things first. One thing it's very essential to understand before we move on, and that is why I told you to keep this process in arrival time, burst time, PID. Okay, it'll take a bit of time. I hope you guys will be with me. Okay, during that. So what we're trying to do is see essentially how are we, if you guys rewind this a bit and if you see how we are choosing process, even in this case we had process P3 and P4 available. P4 is already executed, so that is gone, but P3, P1 is available. What did we do? We looked which has the earliest arrival time, correct? So P3's arrival time was 1, correct? P1's arrival time is what? P1's arrival time was 2. So what did we do? We went ahead and serviced P3. So we are finding out which has the lower available time and not yet executed, and then only we have to move on. Okay, so that is mainly, see, number one, not yet executed, a lower burst time, the lower arrival time. Arrival time is what we looked at in this particular case, okay, because P4 is already executed. But in case all the processes are executed, this thing we can't check. At the same time in Python, we cannot divide the list into two parts, that is not executed and executed part. So we have to do something that still maintains this, whatever the first element is the element that we're going to blindly go ahead and choose. At the same time, we don't have to worry about this whether a process is executed or not, because that is an entirely different headache. So how do we prioritize this? Simple. We see, given this particular list, can you guys agree that this list when we input is random? P1, P2, P3 is just some arbitrary value we're choosing and we're writing it so that humans can understand it better. But in this case, the computer should understand it better. In case the process is there, the lowest arrival time should be given first priority. That means the process should be arranged in what? In order of the lower priority, so that we can just go ahead and take the first element. If not, we have to go ahead, once that process is serviced, we can go ahead and add it to the end. That is not a problem, even though it has a lower arrival time. But in case it's not executed yet, when we take the first element, that will be the lowest arrival time, correct? That has not been executed yet or executed it. That entire executed, not executed thing we're trying to avoid. That's why we're bringing this into the picture, okay? So lower available time should be available, given priority first in case there are two processes in conflict with each other, to see which goes first. To understand that, once you guys get that, what we're going to do is, that's why we have this particular thing there. If we go ahead and sort this process list, okay, if we just do process list dot sort, what do you think will happen? Initially we have P1, P2, P3, okay. What will happen now? See, 0, P4, this particular thing will be first. So this will be the order in which we'll be executing. See, P4, yes, then P3, yes, then P1, yes, then P5, yes, then P2, correct? If you guys can go ahead and you can print this also and see that what is going on. Go ahead and print this process list, okay, and see P4, P3, P1, P5, P2, P4, P3, P1, P5, P2. So that is the what? This is the order in which you're executing. See, initially what happened? We executed P4, correct? Then we threw this back. Then we executed P3, yes. Then we executed P1, yes. Then we executed P5, yes. Then we executed P2, yes. Then the first element will be what? P4 only, correct? This will be P4 only. So again, this will be coming. So we managed to maintain this simply with one particular what? Command. That is why I'm telling you to sort. That doesn't mean our algorithm is completely finished yet. This is just the order. We are just clarifying things a bit better so that we understand what is going on. Okay. So That being said, we can go ahead now and work with the algorithm. Okay, so sort the processes with respect to arrival time. Okay, now we can go ahead and loop this particular algorithm until the process list is empty, as always. Because why? Because if the process list is empty, that means every process is being serviced. Once a process is serviced, the process will be removed from the process queue. Okay, so first things first, what are we doing? If you guys rewind and see, we're seeing if the, let me just go ahead and remove these. Yeah, so what are we checking first? We are checking, this is a boundary condition, we are checking the available process, correct? And we're checking so first things first, we have to address that boundary condition that no process is available. In order to do that, we have to check which processes are available first. Okay, so let us iterate through this process list. So arrival time is given by what? Process of 0, correct? P of 0. What we're saying is, if P of 0 is less than equal to current time, that means this process is available. Okay, okay. Now what else do we need? See, once this is done, we have something called available. So boundary condition 1. What is that boundary condition? No process available. In case no process is available, we can go if available equal to empty. We can go ahead and say that the CPU was idle, and we have to increase the time by 1. See, I hope it's straightforward why we are choosing 1 and not the time quanta. In case you guys don't understand, see, the thing is very simple. Okay, see, if let's say at time is equal to 0, no process arrives, but instead of P4, instead of 0, it comes at t is equal to 1. Okay, so t is equal to 0, it is idle only. But if we take the entire time quanta from 0 to 2 itself, the CPU will be idle, but it should not be idle because at t is equal to 1, process is arriving. So obviously, whenever a process arrives, immediately it should be serviced. Okay, in case the CPU is idle, it should not be idle when there process available. That is why we increase this by the very basic quantity, which is 1 in this case. That's why we're choosing 1. Okay, once that is done, we can go ahead and press continue. So this particular boundary condition is handled. Okay, what do we do if not? Continues there, else is not needed, but we're doing it anyways. So else, what do we do? Available of 0, as we said, process will be available of 0. If you guys want proof on why available of 0, this is the proof. This is why we're doing this. Once we're sending it to the back, the first element always will be in this order. Okay, so available of 0 will be the process. We need to service this process now, correct? Now first things first, we can go ahead and add to the Gantt chart the PID. PID is given by what? Process of 2. Is that right? Okay, so PID, we have added this to the Gantt chart. What do we do next? Next, we have to reduce the burst time. But here there's a problem, because if the remaining burst time in this particular case is less than the time quanta, what do? We have to handle that. So that is the boundary condition 2. How do we handle this particular boundary condition is, if, see, look, if the burst time is given by process of 1, see, we can go ahead and define that as a variable itself. Remaining burst can be given as a process of 1. Correct? If remaining burst time is this, then we update. But before that, what do we need to do? We have to remove this process. You can see we're removing this and putting this back, right? So first of all, let us just remove the process. If we update it, we cannot remove it then. That's why we're removing first itself. Go ahead and in the process list, just remove the process. Okay. Once that is done, update the burst time. We calculate the remaining burst time and we say if the remaining burst time is less than or equal to the time quanta, that means in this particular time interval, the process is going to complete service. So in that case, what we are doing, see, in even this case, the time quanta is 2, but we are only adding 1 to the time value because that is the remaining time for P4. So instead of adding the time value as the time quanta, we add the remaining burst time to the time. Then we go ahead and created a completed dictionary. We add, see, PID is process of 2. We add this at the entry, and let's just say the CT is nothing but the T here. Okay. And we're going to, for now, let's just put T, then we'll go on to the turnaround time and the waiting time. Once that is done, we can go ahead and do continue. Okay. Else, what do we do? If this is not there, update the burst time. If there is more than the burst, if the more remaining burst time than the time quanta, what do? We simply just go ahead and add the time quanta to the current time. We decrease the remaining burst time, that is process of what? The burst time is given by 1, correct? 1. We decrease it by the time quanta and then again Gantt chart already added. And then what do? In this process list, we go ahead and append this process again. That is it. That is the simple thing we are doing. That is what we have been discussing for so far. Okay. So once all of these conditions are handled, that means our algorithm is pretty much done. We can go ahead and print the Gantt chart and followed by the completed dictionary. Okay. I'll go ahead and clear this so you can see it a bit better. See, right now we have P4, P3, P1, P5, P2, P4, P4, P3, P1, P5, P2, P4, then P3, P1, P3, P1, P5, P3, P1, P5, P3, P1, followed by P3. So everything is right. So if you go ahead and check for P3 as well, the completed time should be 23 as it is here. Now we need to find the complete time, the turnaround time and the waiting time. That is why I told you guys to wait over here, because the burst time we are updating right here dynamically. So we cannot use this formula. See, the waiting time, as you know, is given by the, one second, let me just write this down so you guys can understand a better. Waiting time is given by turnaround time minus burst time, correct? So this burst time is being updated constantly. So we cannot use this value to calculate the turnaround time, because as you see, we are only using this value to calculate the burst turnaround time, not the values in between when we are updating it. So what we have to do is simply we'll just keep a copy of everything's burst time first itself. We'll go ahead and create a dictionary called burst times, okay, to keep track of all the burst times of all the processes. We'll just iterate through all the processes in the process list, and then process the PID is nothing but the PID is nothing but P of 2, burst time is given by P of 1. We can go ahead and create a dictionary entry, burst times of what? PID is equal to the burst time. Okay, if we do this, if I go ahead and print the value here to see if you guys can understand what we're trying to do here. Okay, I'll print the burst times dictionary. See, we're just keeping track of all the burst times alone, so that this formula is easier for us to do. See, arrival time will always be constant only, but the burst time is being updated. That means we have this particular copy before itself. It's better for us to process stuff. Okay, so now we can go ahead. So CT is nothing but T, correct? And arrival time is what? Arrival time is nothing but process of 0, correct? And burst time is what? Burst time is burst times of PID. Again, PID here is nothing but process of 2. Okay, so once we have all these details, TT can be given by what? CT minus arrival time. Arrival time, correct? And then what is WT? WT is what? TT minus burst time. Okay, once we do this, we can go ahead and put the entry normally CT, TT, WT, and when we run this problem, we can see this is the same Gantt chart only as before, but for P3 we have all three values, that is 23, 22, 14. We also have 23, 22, 14, which means the algorithm works. Now, if you guys want to display this a bit better, you can iterate through this completed dictionary and put it like a table. If you want to calculate the average waiting time, you can just go ahead, add all these values and divide by the number of processes. If you need to calculate the start and end time for every one of these values, you can go ahead, put this time, put it into a list kind of, and print it with the Gantt chart. That is up to you. Anything from here is just basic print statements, declarations and stuff like that. But this itself is the core of how this algorithm works. If you guys want the code, it will obviously be in the GitHub link. The link will be down in the description. My advice always is to understand this video fully and try to apply this on your own. The idea is very simple. Put the table, work this out, then work out all the boundary conditions, and then just get started with coding. Very simple, very straightforward algorithm. A bit tricky compared to the other algorithms, but still straightforward. I hope this video helps you. If this video helped you, hit the like button. I'll see you in another video. If you guys want more of this series, the playlist link will be down below. That being said, thank you so much for watching. I'll see you in the next video. Until then, bye.